All right, today we're tuning into the cosmos. We're going to listen to some signals that, according to everything we know, just shouldn't exist. These are echoes from the universe's most extreme events, and they are so strange they're making us rethink the very laws of physics.
So let's start with a little thought experiment. Imagine we point a radio telescope up at the sky, and we pick up a signal. It's steady, it's repeating, happens all the time. But what if this signal
Was coming from a spot in the sky where our physics says there should be absolute silence? Well, that's not some sci-fi plot. That's a real story. It actually happened.
And that brings us to our first huge mystery, a radio source with the catchy name GPMJ 1839-10. Think of it like a cosmic ghost story that's been playing out for decades, totally hidden in plain sight.
So this thing sends out a pulse every 22 minutes, just like clockwork. And get this, when astronomers dug back into old data, they realized it's been doing this since at least 1988. But here's the part that makes no sense. That 22-minute spin is 1,000 times slower than a typical pulsar, which is the kind of object we'd expect to send a signal like this. You see, an object spinning that slowly just shouldn't have enough energy, enough juice to create a radio beam. It ought to be completely dead and silent. Scientists literally call this theoretical dead zone the pulsar death valley. And yet, there it is, broadcasting loud and clear from 18,000 light-years away.
Okay, so to really understand why this is so mind-bending, we need a super quick refresh. What in the world is a pulsar?
So picture a star much, much bigger than our sun. It gets to the end of its life, and kaboom, it goes supernova. What's left behind is this unbelievably dense, spinning core called a neutron star. And when that neutron star shoots out beams of radiation that we can see, we call it a pulsar.
And when I say dense, I mean that is a massive understatement. The material inside a neutron star is so squished together that if you could somehow get a little piece of it,
Just a matchbox full would weigh 3 billion tons. Yeah, that's the kind of physics we're playing with here. It's just wild.
So here's how it works. This super dense star is spinning like crazy. It has a ridiculously powerful magnetic field, and that field shoots out beams of radio waves from its poles. Now the key is the magnetic poles don't line up perfectly with the spin axis, so as it spins, those beams sweep across the sky just like a lighthouse. And if one of those beams happens to sweep past us here on Earth, our telescopes see a regular little pulse.
but that incredible clockwork regularity, it's not just some cool cosmic quirk. It actually turns these lighthouses into one of the most powerful tools we have in astronomy.
They are so unbelievably precise, so stable, that they are, for all practical purposes, the universe's master clocks. And astronomers, being the clever people they are, have figured out a way to use this to build a detector the size of our entire galaxy.
You've probably heard of detectors like LIGO, right? These giant facilities on Earth that look for gravitational waves. Well, a pulsar timing array takes that whole idea and blows it up to a galactic scale. It uses the actual pulsars scattered all over the Milky Way as one giant detector. And it's not looking for the sharp pings of black holes colliding. It's listening for the super low-frequency background hum of the universe itself, maybe from giant supermassive black holes slowly circling each other. By timing the signals from 68 of these amazing stellar clocks with insane precision, projects like Nanograv can actually see the fabric of space-time between us and them getting stretched and squeezed by these enormous waves. It is an absolutely ingenious way to take the universe's pulse. But look, impossible signals aren't the only mystery out there. The universe is also throwing explosions at us that are so powerful and so fast, they completely break every model we have for how a star is supposed to die.
They have this clunky name, Luminous Fast Blue Optical Transients, or LFBOTs for short. And they are just bizarre. Imagine an explosion that's up to 100 times brighter than a regular supernova. One that flares up and then just vanishes in a few days, instead of slowly fading over months.
This timeline really shows you how ridiculously fast they are. A normal supernova can take weeks, even months to fade out. An LFBOT is like a cosmic camera flash. It's incredibly intense, super brief, and then poof, it's gone before you can even get a good look.
So for a while, the best theory was that these must be some kind of really rare supernova from a huge star. I mean, the first few we spotted were in the spiral arms of galaxies, right where you'd expect to find these big, short-lived stars. It all kind of made sense. And then, in 2023, astronomers spotted one they nicknamed the Finch. And the location of the Finch it blew that entire theory right out of the water. So where was it?
It was in the middle of nowhere. Seriously. It exploded in the vast, empty void between two galaxies thousands and thousands of light years away from any place a massive star could possibly be. A star that big just doesn't live long enough to wander that far from home. So whatever the Finch was, it wasn't the kind of star death we thought we understood at all.
So we've got a signal that should be silent, an explosion where it shouldn't be. What does it all mean? Well, it means these extreme objects in the universe, they aren't just puzzles for us to solve.
They're messengers. They're carrying information from the absolute frontiers of physics. They're telling us loud and clear that our understanding is not complete and that there are fundamental forces and events out there that we haven't even discovered yet.
And that really leaves us with the most exciting question of all. From pulsars that are too slow to explosions happening in the middle of nowhere, these signals have already upended our ideas about how stars die and about physics itself. So you have to wonder, what other secrets are out there, hiding in the static, just waiting for us to learn how to listen?